So what is the most optimal form of security? In most cases, it is encryption. So how do we encrypt data? Well, one way we could encrypt it is that we could decide on an algorithm. And then both parties must agree on the algorithm. So an algorithm that was used in the past is to say, let's move the characters in the alphabet 2 steps forward. So for example, an A would be encrypted as a C, a B as a D, and so on. So our message would then move. We would send the encrypted message, and the other person would then be able to decrypt it because they knew the algorithm that we were using. Unfortunately, we have the case that somebody finds out the algorithm. And the problem that we have is that how do we tell the other person that we've changed the algorithm? We could obviously get a third party to send the message for us, but what happens if that third party is a spy? Or what happens if that third party is intercepted? We could telephone them, but what happens if someone is listening to our communications? We could send it through the postal service, but again, someone could be monitoring our letters. So it is extremely difficult for us to change the algorithm. Once the algorithm is known, then it is fairly easy for others to intrude on our data. So typically what happens in encryption is that we use a standard algorithm, and everyone knows the algorithm. So how do we keep our data secure? What we typically do is that we publish the algorithm so that everyone knows how the algorithm operates. Then what we do is that we have a special key. And the special key, once the data is encrypted, the only key that can decrypt it is a key that is known by the receiver. Obviously, the size of the key matters greatly. If we have a 1-bit key, then we only have 2 permutations, a 0 or a 1. So it's fairly simple for someone to try each of those keys and decrypt the message. Then if we have 2, we have 4 different keys, 00, 01, 10, and 11. If we keep increasing the size, it becomes increasingly more difficult for the intruder to test all the keys. This is known as a brute force attack, where the intruder tries every key that they can until they find the right one. So the more keys that we put on the bunch, the more secure our data will be. If we look at, say, a 24-bit key, then we have 16 million different keys. If it was taken 1 microsecond for each of those keys to be tested, then you can see the maximum time it will take to decrypt the message will only be 1.6 seconds. In fact, on average, it will be half as much. So we need to know on what type of system our data is being processed on. We can see if we go up to 64-bit keys, we have 1.84 times 10 to the 19. If we find out that someone can decrypt that message in a certain time, then with encryption, we would increase the key size. So the more keys, the more bits that we have in our key, the more secure it becomes. So we must know how long it will take someone with a certain type of equipment to decrypt our message, because each message has a certain, or data has a certain shelf life or time that is still relevant. If an army was to attack a country within 1 week, then the message must be kept secure so that it will not be decrypted inside that 1 week. If it happens that that message can be decrypted after 20 years, then it doesn't matter. So let's take an example. And we all know that computing power typically increases by 100% every year. So in the first year, if it takes 1 million years to decrypt a message through brute force, then the next year it's only going to take 500,000 years. On the third year, it's 250,000, and so on. And you can see that after 20 years, it only takes 1 year to decrypt the message. We could say the same again if it was 1 million seconds. And then we can see after 20 years, it only takes 1 second to decrypt the message. So it is important to know how long the data can be kept secure and for the equipment that it's been used on. But encryption...
Do you want to just put the keys away?
Oh yeah, I need them in a minute, yeah.
Okay. Sorry.
Okay. The scaling that we assume here is that we have one computer and that the processing power increases by 100% each year. But encryption is one of the best scalable distributed algorithms that we can have. Let's say that we have 2 people trying out the keys. Then we can split the keys into 2. One person tries half the keys and the other person tries the other half. If we have 4 people, then we can split the bunch into 4. So it's obviously going to take a quarter of the time to find the correct key. And we can say the same for encryption. If we have 2 computers, then we can give each computer half of the keys. Then it will only take half the time. If we have 4 computers on a network, it will only take 1/4 of the time. If we have 8 computers on the network, it takes 1/8. With technology these days, it isn't difficult to create computers, single computers with millions of processors inside them. And when you think that on the internet we can have millions of computers all on at the same time, and they can easily decrypt from a range of keys. It is well known that in some encryption, it would be possible if everyone in China was to switch on their computer and were given a range of keys, it would be possible to decrypt any encrypted message. So if we look at the range and we take it as the increase in processing power over the years, and also we scale it with the number of processors, then after only 7 years with a 4096 processor array, it only takes 2 years. So parallel processing is obviously a concern when it comes to encryption.